Welcome to this video, where we will explore one of the most important concepts in quantum computing, the qubit. Qubits are the building blocks of quantum computers, but they are very different from the bits used in classical computers. Today, we'll break down the concept of qubits in simple terms, explain how they work, and why they are so powerful. To start, let's recall how classical computers work. Classical computers process information using bits, which can only be 0 or 1. Every program, every calculation, every image or video is ultimately represented as a string of zeros and ones. A bit is simple, predictable, and binary, but it has limits. A classical computer can only process one combination of zeros and ones at a time. A qubit, or quantum bit, is fundamentally different. Unlike a classical bit, a qubit can exist in a state of 0, 1, or a combination of both at the same time. This combination is called superposition. To visualize it, imagine a spinning coin. While the coin is in the air, it is not strictly heads or tails. It is in a state of both possibilities at once. Only when it lands does it show a definite result. Similarly, a qubit in superposition holds multiple possibilities until it is measured. Superposition allows quantum computers to perform many calculations simultaneously. If you have two qubits in superposition, they can represent 4 states at the same time. 3 qubits can represent 8 states. And the number of possibilities grows exponentially with each additional qubit. This is why quantum computers have the potential to solve complex problems much faster than classical computers, which must handle each possibility one by one. Another important property of qubits is entanglement. Entanglement occurs when 2 or more qubits become linked, so that the state of one qubit depends on the state of another, even if they are far apart. If you measure one entangled qubit, the other qubit's state is instantly affected. This connection allows quantum computers to coordinate qubits in ways that classical bits cannot, enabling incredibly powerful computations. Qubits can be implemented using various physical systems. Some qubits are made from superconducting circuits cooled to near absolute zero. Others use trapped ions suspended in electromagnetic fields or photons of light manipulated with lasers. No matter the physical form, all qubits share the same key properties: superposition, entanglement, and the ability to perform quantum operations through quantum gates. Quantum gates are the operations that manipulate qubits, similar to logic gates in classical computing. But unlike classical gates, which handle bits in a definite state, quantum gates operate on qubits in superposition. This allows quantum computers to process multiple possibilities simultaneously, rather than one at a time. A sequence of quantum gates forms a quantum circuit, which is the quantum equivalent of a program. Measurement is a crucial part of working with qubits. When we measure a qubit, it collapses from its superposition into a definite state of either 0 or 1. Quantum algorithms are designed to manipulate qubits so that the correct result has a high probability of being observed when measured. This probabilistic nature of qubits is very different from classical bits, which always produce the same result. Working with qubits is challenging. They are extremely sensitive to their environment, and interactions with heat, vibration, or electromagnetic noise can destroy their quantum state. This phenomenon is called decoherence. Scientists are developing techniques to reduce errors, protect qubits, and extend their coherence time. But building stable, large-scale quantum computers remains a major scientific challenge. Despite these challenges, qubits are at the heart of the potential of quantum computing. They allow us to explore enormous numbers of possibilities at once, perform calculations that are impossible for classical computers, and tackle problems in chemistry, cryptography, optimization, and more. Understanding qubits is the first step toward understanding how quantum computers can transform the way we compute. In summary, a qubit is a quantum version of a classical bit, but it can exist in multiple states simultaneously, become entangled with other qubits, and be manipulated through quantum operations. Superposition, entanglement, and probabilistic measurement make qubits both powerful and delicate. They are the foundation of quantum computing, enabling computations that go far beyond the capabilities of classical systems. By understanding qubits in simple terms, we gain insight into the principles that make quantum computing so revolutionary. These tiny units of quantum information carry the potential to solve problems that were once thought unsolvable, from simulating molecules to breaking encryption, and even to advancing artificial intelligence. Thank you for joining this exploration into the world of qubits. As we continue to learn more about these quantum building blocks, we come closer to a future where quantum computers may change the way we understand and interact with the world around us.